Okay, so I'll review a little bit from last lecture and then start from there. So what we were talking about was side chain recovery or protein core repacking. And so the idea there is an experimental protein structure is obviously made up of amino acids, and the side chains will have certain conformations that are experimentally determined. And the idea is if you take those side chains off or sort of forget what the experimental values were, can different types of force fields analyze the surrounding structure and find out what side chain conformation should be placed there. And then you can compare what the force field predicts and then what the actual experimental structure gave. And you can do that for core residues that are buried in the core, or you could do surface residues. And so we're going to focus on core residues. And as I highlighted in this snippet from a recent paper on a review of sidechain recovery, a lot of folks in the community use force fields that have lots of different terms, so they're very complex. And so this particular paper lists 8 different types of contributions to the force field. And in this set of slides, I was going to argue for a much simpler approach where you focused on what I called the stereochemistry of a protein and then atomic overlaps. And this approach is similar to what Ramachandran used in the early studies of backbone dihedral angles. And so the protein stereochemistry are respecting the covalent bonds between two adjacent atoms, and then the bond angles that are formed among 3 mutually covalently bonded atoms. And then that's what I've been calling stereochemistry. And then the overlaps are between non-bonded atoms. So atoms that are separated by 4 or more. So above a string of 3 atoms are what I'm calling non-bonded. And so the energy function that I was suggesting for the non-bonded pairs of atoms was this. It's called a purely repulsive Leonard-Jones potential. So Leonard-Jones potential is used in protein force fields to mimic dispersion forces or van der Waals interactions between atoms that don't have charge. And so in general, Leonard-Jones interactions have repulsive contributions and attractive contributions, but we're just going to consider the repulsions. So this is if one atom is, if a pair of atoms are overlapping each other, so their separation is less than the sum of their diameters, then the average of their diameters, then there's going to be a repulsive force that pushes those 2 atoms away from each other. And so that's what this top equation is. And so we basically can evaluate this energy for all pairs of atoms and get a value of the energy. And then we can Boltzmann weight it to basically take the exponential of the total energy divided by the temperature to find a probability distribution for having a particular atomic configuration. And in this case, it would be for having a particular sidechain dihedral angle. So then I promised these movies. So here's a simple example and this is focusing on intra-residue interactions. So we only have this leucine residue. It's taken out of a protein, and what we're doing is fixing, leucine has 2 side chain dihedral angles. We're fixing the chi-1 conformation and then varying the chi-2 part over 0 to 2 pi. And so then you can ask, well, what are the non-bonded overlaps, or what's the energy of the system as I rotate through this 0 to 2 pi for the second dihedral angle. And you see that the energy varies, but the conformation of 180 degrees is the lowest energy. So in this way, we would say that this 180 degree conformation is the one that's preferred in this case. Then I talked about the way we chose to pick our atom sizes, which determines the overlaps between atoms, was through this approach where we would vary all possible combinations of the radii and then find the, and then use the atomic sizes where the predicted side chain dihedral angle distributions match those from experimental structures. And in this case, we focused on the dipeptide model where we only had intra-residue atomic overlaps, not the model where each residue is in the context of the protein. And we basically said, are the rotamers that are selected those that are found in X-ray crystal structures? And then we would rely on the model in the context of the protein to pick out the particular, the exact conformation that's seen in the experimental structures. So this is a figure that's illustrating that point where the left plot is the experimentally determined side chain dihedral angle probability distribution for isoleucine in crystal structures. There's this rotamer number 6 that's very probable, and 3 and 4 are also relatively probable. And then the right plot is the result of varying the atomic sizes and picking the sizes that reconstruct the rotamers. And you see that they do pick out the general features of the rotamers, but they don't get the probabilities in each bin correctly. And that's because this is a dipeptide prediction. It's not in the context of the protein. And we're thinking that if you put an isoleucine in the context of the protein, it'll be able to pick, the model will be able to pick the exact conformation that's seen experimentally. And so that's what's shown here. Here we have on the right-hand side a prediction for a particular isoleucine, so isoleucine 56 in a particular crystal structure 2NWD in the protein data bank. The color represents the prediction, so that's the probability distribution that we're finding. And the green X in bin number 5, that's in the center, near the center of bin number 5, is the experimental value for isoleucine 56 in 2NWD. And so you see that the prediction of this model is pretty good. And so what we can do, and I'll show you in a couple slides, is that we can pick the most probable region of that orange, red, black probability distribution, and then compare that value to the experimentally seen value to get an error in the prediction. So then I walked through a few other amino acids. So phenylalanine, the prediction from the dipeptide model, again, just shows that it's relatively rotameric. So you can You could get rotamers 1, 2, and 3 for Chi1. But then when you put a particular phenylalanine in the context of a protein, you get a very specific prediction. And so again, the dipeptide model gives the general rotameric features, but it doesn't pick a particular rotamer for phenylalanine. But then when you look at the context of a particular structure, then there's a particular rotamer, number 3, that is selected because that rotamer doesn't cause inter-residue overlaps, atomic overlaps. Again, in valine, the dipeptide result gives 3 rotamers at 60 degrees, 180 degrees, and 300 degrees. Whereas when you put a valine in its protein environment, a single rotamer at 60 degrees is selected, and the vertical dotted line is the experimentally determined value. So since the model is predicting the side chain conformations of each individual amino acid, when you average them together, you get very good quantitative agreement for the full distribution. And so this is the full distribution of isoleucine from the model in the context of a protein, that's on the right, and then the experimentally determined probability distributions on the left. And you see there's quantitative agreement that, for example, rotamer number 6 is selected 73% of the time in both the model and the experimental distribution. So with that, here's another way to show those results. So what we can do is we can take each residue type, so that occur in protein cores, say isoleucine, leucine, methionine, etc. And we can say we're going to look at those residues in protein cores, and so we can generate a prediction from this hard sphere stereochemical constraint model. And on the bottom, there's a metric which determines the success of the prediction. So in this case, the chi with the superscript HS, which stands for hard sphere, is the result of the prediction. And then the chi crystal is the experimental value. And so for a given residue, it'll have either just a chi1 or a chi1, chi2, or chi3 based on how many side chain dihedral angles that residue has. And so you can get a metric of the success of the prediction by just calculating the root mean square deviation. And so isoleucine has 2 dihedral angles, and now you see the fraction that this is a metric of success. You find out the fraction of isoleucine residues that you predict within a delta chi of 10, 20, or 30 degrees. And so obviously, as you make the metric of success less stringent, as you go from 10 to 30 degrees, the probability increases. So you see that for most residues, if you look at the 30-degree metric of success, for most residues, 90% of the time, you're getting an accuracy of within 30 degrees. One reason to pick 30 degrees is that's the typical width of a rotamer bin. So if I go back here, so for example, you have the 180-degree rotamer in the central region for valine, and then you can see it's roughly plus or minus 15 to 30 degrees. And so if your error is 30 degrees or less, then you're able to pick the correct rotamer. So you can see that for most residues, isoleucine, leucine, phenylalanine, threonine, tryptophan, tyrosine, and valine we're all getting very accurate results. 90% and most of the time 95% or above success for being able to predict the sidechain conformation. But there are two notable exceptions. One is methionine. The problem with that is it has 3 sidechain dihedral angles, and the third one, the chi3, is notoriously very difficult to determine from X-ray crystal structures. It's the electron density is noisy or fuzzy there, and so it's known that methionine is, the chi3 is difficult to predict. So if we leave off chi3, then methionine goes back up to 90%. And another notable exception is serine, and the rationalization here is that serine and threonine hydrogen bond, and threonine is more bulky than serine, and so threonine can hydrogen bond, but the hydrogen bonding is not necessarily necessary to determine the sidechain conformation because it's so bulky, whereas serine is not very bulky. The sidechain is not as bulky as that for threonine, and so maybe hydrogen bonding is necessary to determine the sidechain conformation of serine. So then what we can do is compare our results to other sidechain recovery software. And so that is here. So it's a similar plot, the fraction of residues that you can predict to within a certain value of delta chi. So for here, we just show it for 30 degrees. So these results are the fraction of residues that you can predict within 30 degrees. And we can compare this hard sphere plus stereochemical constraint model, that's in red, to Rosetta, which is a commonly used sidechain recovery software. And so what you can see is that the red and the yellow are comparable. In many cases, the red this simple model does better than Rosetta on on a lot of the residues, but there's a notable exception, which is serine, which is consistent with what I said on the previous slide, that Rosetta does have a term in the force field, which deals with hydrogen bonding. And so it's presenting this interesting result that to determine the sidechain conformation of serine, looks like you do need to consider hydrogen bonding, whereas for threonine, you don't. But for all others, it looks like the dense packing in core residues in these packing constraints are sufficient to determine sidechain conformation in the cores of proteins. So I think that was published, and the community knows about it, and that's great. And so what we can now think about is that we have well-defined atom sizes for definitely our hydrophobic residues. And so since the atoms have definite sizes, they're starting to look like these physical objects. And so I can talk about the packing fraction, which is if I have a container and I put these objects in the container, how much of the volume of that container is taken up by the objects. And the packing fraction has been studied for a very long time, and so we know how different shaped objects pack in various containers, and we know how particle shape and the various types of crystals, crystalline arrangements affect the packing fraction. And so that's what we're going to do in the going forward in this set of slides. The work really started in terms of trying to understand how cores are packed with Fred Richards of Yale in the mid-70s and then continued into the 80s. And then I already mentioned this paper by Ken Dill and Liang, where they ask, are proteins well packed? This is sort of a survey of the literature from the 80s and 90s. So the packing fraction of a residue I call phi sub r. And that's the volume of a residue divided by the volume of a container. And the container is always the difficult thing to define. So the volume of a residue, I'm thinking of this residue as made up of a bunch of spheres, and so I can think about calculating the volume of a residue. But the question of the container is like, what is the container? What is the residue in? And so we'll talk about that in a second. And so then you can calculate the packing fraction of residue. And then if you have a core, you could just take, so you have a core that's made up of a bunch of core residues, and then the packing fraction of the core of this protein would just be the average of the packing fractions of the individual residues that make up the core. So here's this idea of a container. And so here I have, these are dots, but let's just think of these as, so these are dots in 2 dimensions, so on a flat surface, but think of these as little spheres. And so in 2 dimensions, and if you have spheres, what you can talk about is a Voronoi tessellation in 2 dimensions, and it's rather easy to construct. You basically just need to look at the connections. So you take an individual sphere and you look at its nearest neighbor connections. So you draw lines between a given little sphere and its neighboring spheres. And then you draw all the perpendicular bisectors to those connections. And those perpendicular bisectors will form a polytope, which is just a closed polygon or polyhedron. And so in 2 dimensions, it's these different polygons. And so so what that polygon represents is the region of space that's closer to that particular sphere than any other sphere in this drawing. And so that's a good container. So the container represents the boundary of the points that are closest in space to you. And so that's what we're going to use as our container. And so you can do this in 3 dimensions, and you can do it for not just spheres, but you can do it for arbitrarily shaped objects. When you do it for arbitrarily shaped objects, you want to do more like a surface Voronoi tessellation, which instead of using the center of a particle, you look at the distances between surfaces, and then you find basically the bisectors to those surfaces, the sort of median surface between neighboring surfaces, so a mean surface. So when you do that, when you look at a Voronoi tessellation, which is trying to find, the region of space that's closest to a particular surface than any other points in space, looks like this. And so here I have a residue, which is made up of all of the atoms in that residue, the backbone and the side chain. And then I show the tessellation in the pink region. And so the points in space that are in the pink region are closest to this particular surface of the residue than any other surface, than the surface of any other residue. And so then it's clear from this diagram that I can calculate the packing fraction, which would be the volume of the residue divided by the volume of this complicated geometrical object, which is in pink. So just a comment about the volume of the residues. So here I show you a few examples of the residues with their correct radii. And so what we want is I'm going to sneeze, hold on. Sorry. So I want the basically non-overlapping volume. So these objects are composite objects made up of spheres. So like I have hydrogen atoms, I have carbon atoms, I have oxygen. Sorry, one more sneeze. I can't guarantee I won't sneeze one more time, but it's not going to persist that much longer. But anyway, the residues are made up of a bunch of spheres. So they're composite objects made of spheres, but I want the non-overlapping volume of the spheres. So so you can calculate that. It's basically you calculate the volume of each sphere, but then you don't double count the overlap between the spheres. You only each pair of spheres you only count it once. So I show you a few examples of the volume, this non-overlapping spherical volume for leucine. So it's 88 angstroms cubed. And so here you can sort of get a feeling for the bigger residues compared to the smaller residues. So for example, phenylalanine is 100 angstroms cubed, where glycine, which doesn't have, has a negligible side chain, is only 30 angstroms cubed. So the backbone basically takes up around 30 angstroms cubed, and then all the rest of the volume goes into these bulky side chains. And so here's a really nice result about the packing fraction of the core. So you have experimental proteins, the experimentally determined proteins. You can identify which residues are the core residues by looking at the relative solvent accessible surface area. And then you can go through the procedure that I outlined in the previous slides, and you can define the packing fraction of the core of those core residues. And so those results are in blue. And so we just index it by the number of residues in each protein just to space it out. And so you see that the packing fraction is around 55, 56% for the larger proteins. The problem with the smaller proteins, say 20 and below, is that they don't have very large cores. So maybe it's one residue in the core or two residues in the core, and then you're going to get large fluctuations depending on which residue is in the core. So if it's a glycine, it's actually going to be very dense, relatively dense, whereas if it happens to be a phenylalanine, it could be not as dense because of the side chain, and there's sort of nothing to fit against it. But as you go to larger proteins and you have more well-defined cores, you get 55, 56%. And then I compare that to Ken Dill's results. And there are two main differences between Ken Dill's results and our results. One of those differences is not the set of proteins. We studied the exact same set of proteins. It was in the modeling approach. So for example, in his modeling approach, he used an extended atom where he didn't have explicit hydrogens. But the main distinction is that his atomic sizes were not ours. So in fact, he didn't do anything to calibrate his atomic sizes. He just sort of used standard sizes, which were in the literature. So to some extent, he just sort of randomly picked his atom sizes. And when he does that, the atoms have significant overlaps between non-bonded atoms. And when you have significant overlaps between non-bonded atoms, it's not even really meaningful to calculate the packing fraction, because packing fractions are really most well defined if the objects don't overlap each other. So like if you're calculating the packing fraction of bubblegum balls in a bubblegum machine, the bubblegum balls don't overlap each other, and so you can calculate the packing fraction, how much of the container do the gumballs take up. But if the gumballs, for whatever reason, could pass through each other, then it's not really meaningful to calculate a packing fraction. And so that's why he gets this different result. He got between 70 and 73, and that's what led him to believe that the cores were as densely packed as crystal structures, because crystal structures, one of the most common crystal structures is the face-centered cubic structure, which is 74%. But the real result is 55 or 56%. And I'll show you why I think that our result is more meaningful, our particular number. Here's just an example of the different type of modeling. You see on the right is the explicit hydrogens, and the extended atom model using Ken Dill's radii shown on the left, you can see you don't get some of the fine scale structure from the hydrogens when you use the extended atom model. And his residues were bigger, had more volume. You see Ken's leucine volume is 107 angstroms cubed, whereas with our atom sizes, they're 88. So they sort of fit into the core better. And so why did I make this comment that, you know, the number 55 or 56% packing fraction in the core makes sense? Isn't that too low? You know, can you have side chains that pack densely and are sort of constrained so that they don't sort of, that they're not able to sample other conformations, that they're kind of locked in? Is 55, 56% dense enough to lock in the side chain conformations? And so the way we're going to get intuition for this result is to carry out a simple packing study. And you could do this by 3D printing amino acids, you know, using a 3D printer. So sort of making macroscopic models for the shapes of amino acids. So what we're going to do is have amino acids that are typically found in the core and take on backbone and side chain conformations that are seen in proteins. And then we're just going to pack them together in a box. And of course, that's not available. So this one is very important. So I'm going to have to find this one. Okay, I found it and I'll show it. Okay, I'm just playing it a couple times so you can get the idea. So again, what we do is we randomly place residues in a box. These residues are, the types of residues are those that are commonly found in cores of proteins. These particular ones are rigid shapes, so we don't let the side chain and backbone dihedral angles vary, but that's a current interesting research direction. But basically what you do is you put them in the box. In this case, we grew the residues, so you can actually see the residues growing, but that's similar to having the box shrink and, you know, compress it, which is what would happen in a, you know, as the protein folds. And so then what we do is we can do that type of experiment or simulation, you know, thousands and thousands of times. And then we can ask, well, what's the packing fraction that I get when I'm jamming these into a box? Okay, so then I think you guys can see this. And so the results of those packing simulations are shown on the same plot as the results from the true experimental structures. So the values of the packing fraction in the cores of real experimental structures. So those are solid lines, the experimental data, and then the packing simulations that I just showed you a few seconds ago are in the dashed lines. And so you see that there's a really nice agreement that the peak is somewhere around 55 or 56%. And so what the proteins seem to be telling us is that that number is not too small, that if you imagine amino acids as particles that have these very interesting shapes that are a little bit bumpy and irregular, that if you physically pack them in a box, 3D print them and pack them in a box, they'll typically form structures that are around 55 or 56%. And that seems to be what protein cores are doing as well. And so some of the outstanding ideas are two. Is the things that weren't included in the simulation are the fact that proteins do fluctuate with temperature. And so, for example, they could be at physiological conditions, so room temperature. And so there are proteins the conformations do fluctuate. And so that was not included in the simulation. And it's well known that the exact protocol that you use to jam or to compress and find a packed structure can depend on the algorithm. And so if you included thermal fluctuations in the algorithm, could you get a denser answer? Another thing that wasn't included, which is still a mystery that we're working on, is that proteins, have a backbone that's connected. So each amino acid is connected to another amino acid by a peptide bond. And, protein folding definitely involves the collapse of a chain, not the compression of individual amino acids. And so does the fact that there's a polymer chain, a connected backbone, affect the packing fraction? On the one hand, the results, the agreement between the disconnected packing and the protein suggests that the connected backbone doesn't play a role, but there may be sort of these competing effects where if we added in thermal fluctuations, that would increase the packing fraction relative to our current result, but maybe the results of including a backbone would shift the packing fraction results down, and you would get what we're getting now. So this is an active area of research. Just a quick comment that we can also measure how the packing fraction decreases with as you move away from the core. So if you look on the right of this plot, this is the packing fraction as a function of the relative solvent accessible surface area, which varies from 0 to 1. So you can see here that there's some structure in this. So as you go to very small values of R-SASA, so below, say, 0.05, you reach the 55, 56% that we were talking about. And then there's a strong decrease, say, below 0.1 R-SASA. So this may be a good way of defining, the core versus the surface, because you can sort of see a kink in the behavior of the packing fraction versus the relative solvent accessible surface area. So then for the remaining time, I'm going to try to talk about this, this idea of physical insight into packing fraction, that the packing fraction has been studied in physical systems for a long time. And so people have intuition for the relationship between particle shape, different types of crystal structures, and the values of packing fraction that you get. And so we can try to physically motivate why the packing fraction is not 74% and is much closer to 55%, and why we do expect that. So the first thing that we can talk about is what's called the bond orientational order parameter. And so what you can do is come up with parameters that tell you how close you are to a crystalline structure. So if you have a low value for this parameter, you're disordered and you're not near a crystal structure. Whereas if you have high values, you're close to a particular type of crystal structure. And so one way to do it is that when you're a central atom I or a central particle I, and you are in a particular crystal structure, the atoms are in well-defined places. You know, when you look off in a certain angle, you'll find, a certain direction. You're supposed to find an atom, or if you go off in some other direction, you're not supposed to find a particular atom. And so you can talk about different types of symmetry. And so different crystalline structures will have the atoms arranged in your environment that obey different types of symmetries. And so what you can do is use the spherical harmonics, which basically tell you about this type of symmetry in spherical coordinates. And so one thing you can do is look at for 6-fold symmetry or 12-fold symmetry, and that tells you, how the atoms are arranged. The 6 and 12-fold symmetry are consistent with what's called face-centered cubic crystal structures, and those occur in lots of metals and other systems where the constituents that make up the solid are made up of spheres. So it's a very, this type of crystal structure occurs when the constituents are spherical particles with very isotropic interactions. So you can imagine stacking, if you stacked oranges in an FCC. So for example, oranges, which are spheres, roughly spheres, can form these face-centered cubic structures, and then you can look for Q6 order, and it'll be large. So there's a well-known relationship between this order parameter, Q6, which is this 6-fold bond orientational order parameter, and the packing fraction. And this idea is pretty simple. It just says if you're in a crystal, you can pack more efficiently than if you're in a random arrangement. And this is still somewhat of a mystery of why crystals pack more densely than random structures. In fact, so for spheres, this has been proved that the FCC crystal structure is the densest packing of spheres in 3 dimensions. It's been proved. So there's no random structure of spheres that can pack more densely than 74% for FCC. But for other types of particle shapes, for example, for an ellipsoid, it's commonly known that crystalline arrangements of ellipsoids pack more densely than disordered, but it hasn't been proven. And so, for example, there's a quest for being able to find a disordered arrangement that packs more densely than a crystalline arrangement, and it's still possible for non-spherical particles. But here we're talking about spherical particles, and so there's a well-known relationship between order and packing. So the most dense packing you can get, I just said, was 74%, and that corresponds to a Q6 value of around 0.5. So just if you calculate the formula that was on the previous page, you get around 0.5 for a perfect FCC. And then it's also well known that if you go to completely disordered systems, the lowest density that you can have and still have a solid-like state is 64%. So the range, is around 5%. You can go between 64 and 74 and have a solid-like structure of inert spheres. And then those two regions connect through the order parameter. So for example, at the lowest values of packing fraction, it's very disordered, so 64. But as you increase in packing fraction, there's a monotonic increase in the order parameter. So the only way that you can get a very dense packing in the 70s for spherical particles is have it being ordered, which is not what protein cores look like. Protein cores are not extremely ordered structures. There is some order in the sense that you do have secondary structure like alpha helices and beta sheets, but they're not all sitting on this crystalline lattice in the cores of proteins. Another thing that Dill and others looked at when considering the packing fraction is they said, oh, well, the atom sizes are not all the same. So in this particular slide here, I'm talking about all the spheres are the same size. So when I was talking about theorems to prove the densest packing, so far it's only been done for the same size spheres. But what happens if I have different size spheres? So what you can do is all the atoms have different sizes. So sulfur is the biggest, carbon is fairly big, but then hydrogen is small. And so you can look at the range of atom sizes in the atoms that make up proteins, and then you can try to pack those. And so we did that for disconnected atoms. So we looked at what's the exact size distribution and then the population distribution of those atoms, and we just packed them together, but saying they're non-bonded. So the spheres with different sizes can move around. And we found that there's no real difference with random packing of same size spheres. So just the very fact that the sphere sizes are different doesn't cause a big difference in packing fraction. You still get 64% that you would get for monodisperse disconnected spheres. Whereas the amino acid packings get, a peak at 55, 56%. So then the next thing you can consider is particle shape. And so that's what this figure is describing. It's looking at, well, what different packing fractions do you get if you vary the particle shape? So the first set of data I'll describe are the top curves. So there's like a solid curve, black curve. There's a dashed and dotted curves. And so we're looking at the packing fraction, and the horizontal axis is the aspect ratio. So now I'm going to ask a similar question. When you pack non-spherical particles together, what results do you get? So you can pack ellipsoids, spheros. So an ellipsoid is an ellipsoid. It has, it can have, it has different axes. We're going to talk about, ellipsoids where there's one. So in principle, you can have three different axes that have three different semi-major axes, so like A, B, and C. But you could also do where B and C are the same, so there's an axis of rotation. And right now we're going to talk about prolate ellipsoids. So they look more like footballs than oblate ellipsoids, which are pancakes. And so then you can also talk about spherocylinders to mimic elongated particles, where spherocylinders are made up of a cylinder and then spherical end caps. And so then again, you can talk about, an elongated particle. And so then the aspect ratio just means how do those differ from spheres? So how elongated are they? So for an ellipsoid, it could be the ratio of the major to minor axis, or for a spherocylinder, it could be a ratio of the length of the cylinder to the radius of the end cap. And so what you find is somewhat interesting structure that you get sort of a minimum at the sphere value. So at the sphere value, you get, around 64%, as I discussed before. Then it increases. So it shows that as you elongate particles a little bit, you can fit the elongated particles in the gaps between other particles. But then as you elongate them more significantly out to like 2 or 3 aspect ratio, they don't pack together as well. And so that's our expectations from like spaghetti or pasta, that if you put those in containers, they don't pack extremely efficiently. And so the aspect ratio range that I'm considering are those that are relevant for amino acids. So what you can do is you can look at amino acids and calculate their aspect ratio by, say, for example, finding a best ellipsoid fit around a particular amino acid. So for glycine, since that doesn't have a extensive side chain, glycine is more spherical, whereas if you looked at methionine, which has 3 side chain dihedral angles, that can be more elongated. And so that's what those symbols, different symbols with large air bars represent. And those are the typical packing fractions that I get from particular residues in X-ray crystal structures. And the air bar, so the air bars just represent the air bar and packing fraction over, all crystal structures and all cores. And then the air bars and the aspect ratio give the different, side chain conformations. So some side chain conformations can be more compact than others, and so you can get fluctuations. And so you see that the aspect ratios for these different types of core residues can go anywhere from 1.25 or 1.3 all the way up to 2.5. And so that's the relevant range of aspect ratios. So what you see is that smooth, the line data doesn't match the packing fraction data of the residues. The data for the ellipsoids in the spherocylinders is much higher. And so that has to do with smoothness. So that data was for smooth ellipsoids and smooth spherocylinders. There was effectively no friction. They were very smooth surfaces. And so then what the colored symbols represent are adding friction to the ellipsoids or spherocylinders, or for that matter, spheres. And so the way that we do this is by adding bumps to the surface. And this is a la, hydrogens. We saw when we look at the amino acids in these 3D rendering, we see that the hydrogens in some of the smaller atoms look like they add bumpiness to the particle shapes. And so that's what I've done for each ellipsoid, for each ellipsoid, I've added different degrees of bumpiness. And as I increase the friction coefficient, I go downward in packing fraction. And so here you can see that I can basically match the bumpiness to at each aspect ratio to a particular amino acid. And so those studies were carried out using shapes that look like this. So in panel A, I have like a spherical particle where I've added bumpiness. And so I can decrease the packing fraction of spherical particles by adding different amount of bumpiness. So for A and B. And then for panel C is this bumpiness that I can add to ellipsoidal particles. And so C is a relatively smooth ellipsoidal particle. And then in D, I have the very bumpy ellipsoid. And then E, F, G, and H are particular realizations of amino acids, and you see that indeed they are very bumpy and are reminiscent of the structures, the bumpy structures in the row above. And so what you can see is that if you're looking for a shape to, as a physical representation of an amino acid, a single smooth sphere is definitely not a good shape to try to get physical intuition about dense packing in protein cores. If you were thinking of ellipsoids, you say, well, amino acids aren't spherical particles, maybe they're a little elongated. Again, just an ellipsoid is not, a smooth ellipsoid is not a good shape to have in mind. And so it seems like the good physical picture is to think of it as an elongated yet bumpy or frictional, as it were. That would be a reasonable physical model for the geometrical structure of an amino acid. So with that, I'll conclude this slideshow and this sort of section of protein core packing by stating these conclusions. So the previous calculations of packing fraction in the range of 70 to 74 by Ken Dill and a lot of others, where they use the extended atom model for proteins, are likely too high. And the reason why this mistake was made is because there was significant atomic overlap in their models, and the physical intuition of a packing model is that these dense values of 70 to 74% packing fraction are too high, that typically physical systems that have such high packing fractions have to have a significant amount of positional order of the structure if you get that high. So instead we predict values in the mid-50s where the atom sizes are well calibrated so that there aren't significant overlaps between particles. And the nice aspect of our calibration was that we were able to predict, using these atomic sizes, the side chain dihedral angle distributions observed in protein crystal structures. So I'll just pause for a minute here for questions, and then okay, and I have around 10 minutes left. So in the 10 minutes left, I'll just try to, again, motivate why using this type of model, the hard sphere plus stereochemical constraint model, would be useful for protein structure, computational protein structure prediction. And so I hope you all can see these slides. And so I'm going to motivate it through 4 aspects. And they go in order of difficulty. And so I think that this model, the hard sphere plus stereochemical constraint model, will be useful for general protein folding, but that is the hardest application. The second hardest is assessment of models, so sort of protein decoy detection from protein folding competitions. Another aspect is, which this model may be useful for, is mutations to amino acids. So for example, you have a wild type protein, then you make a mutation to a core amino acid. Can you predict the conformation of the mutated residue, and does that mutation disrupt structure nearby? or even larger scale structure changes like maybe destabilizing the protein. And then the sort of easiest one, which we already solved, is that we do think that this model, the hard sphere plus stereochemical constraint model, can do side chain recovery or side chain repacking. So in terms of evaluating models from protein structure, protein folding competitions, I can move to the results on this slide. So our expectation is that, based on all of the results that I talked about today, where, we analyzed protein cores and we found certain features in experimentally determined proteins, we could say that we can sort of evaluate models based on their ability to recapitulate those features of protein cores. So just to say it again, most of today's talk, we're saying, here are the features of the cores of experimentally determined proteins. This is what nature does. And so what we can do is evaluate computational models, using the features that we studied or that we found in experimentally determined crystal structures. So that's what we're doing in this slide. We have the overlap energy on the so we're going to first talk about panel A. And so on the vertical axis of panel A we have the energy of overlap between non-bonded atoms. And so in general, we found that protein cores do not have significant overlaps if we use the atom sizes that we calibrated. And then on the horizontal axis, we have the packing fraction. And we found that in protein crystal structures, the cores are around 55%. So in that sort of two-dimensional plot of, two-dimensional feature space, we can plot the experimentally determined structures. Those are the black dots. So the black dots, sort of this blob, and the energy is fairly low. It's definitely below 1. So you have 10 to the 0 or 10 to the 1. Most of the black dots are below that threshold. And then packing fraction, most of the black dots are below 0.6. And so that's the basically spread of the experimentally determined crystal structures, and it's consistent with the story I presented today. Not a lot of overlaps and packing fractions in the mid-50s. The models from the CASP competitions are in the colored symbols. And so there are some colored symbols that overlap the black. You can't see them because they're overlapping the black. But there are an awful lot of models which do not match the experimental structures. So for example, you can have very large energies, orders and orders of magnitude overlap energies. So 4 orders of magnitude easily, 6 orders of magnitude higher in atomic overlap energy. You can have packing fractions that are enormous, that are approaching 1. And so what this is showing is that the models can have significant atomic overlap. They can have significantly high packing fraction, and thus they're probably not very good models. So the other features that you can use to assess, or at least one other, is in panel D. So panel D is the fraction of core residues in an experimental structure or in a model. And the experimental data are these circles with the black outline. And so what you see is that there's a peak around 7 or 8%. So 7 or 8% of globular proteins are core residues. Whereas the models are all the other symbols. And so they don't have a peak of 7 or 8%, they have a peak at 0. So what this is showing is that the core residues, that there aren't enough core residues in the models. And so if you had more core residues that had the right packing fraction and didn't overlap, you would be more closely modeling core residues in real experimental structures. And so what we did is we built a filter. So we basically sort of used machine learning approaches, and this is a very simple sort of classification scheme to try to predict the GDT. So remember, the GDT is the global distance test, and what it is just a score between 0 and 100, which tells you how close was the computational model to the experimental structure. And so what we did is, based on the features that are present in experimental structures, we built a filter which said if you're in the range of, for each feature, which, and the features could be the overlap energy, the packing fraction, the fraction of core residues, and a few other features that describe how densely core residues pack in experimental structures. If you pass the filters that are set up for the experimental structures, so if you pass 100% of those filters, what is the average GDT of those structures? Or if you pass 80% of those filters, then what are the GDT values? And so what you see is that the structures, if 100% of your structures pass those filters, then you get a very high average GDT, whereas if you don't, you get a very low GDT. So this is encouraging that it looks like we can do a very simple classification to identify decoys just by looking at the core residues. So we did I'll finish up with this. We also did a sensitivity analysis, or a feature importance analysis, where we tried to identify which feature was most sensitive. And we found that the basically what that was most sensitive was, could we detect which particular residue went in the core? And this is still a difficult task, is that we can still find sort of false positives where the particular residues that are in the core of the model have the correct packing fraction, overlap energy, and other features, but they're not supposed to be there. And so what we found from this study was we still need to do a better job of being able to predict which particular residue goes in the core. And then once that residue is in the core, then it will have these typical features of a packing fraction of 55%, low overlap energy, a particular number of neighbors, and so on and so forth. So with that, I finished today's lecture. On Monday, we will go move away from globular proteins and go towards intrinsically disordered proteins, and try to identify what type of computational model is best for modeling the properties of intrinsically disordered proteins. And for that, it's going to be basically the radius gyration and the inter-residue separations. And I'll just pause for a moment for questions. Okay, with that, I will see you on Monday at 1 o'clock.